John Wesley Hyatt was a scientist who loved to compete. He became involved in a contest to invent a substitute for ivory that was used for billiard balls. Taking his cue from earlier research, he invented a ball that would not break. He pocketed the $10,000 prize and invented celluloid, the first ever plastic. In an effort to improve our daily lives, scientists are always looking to come up with new and better materials. Back in 1935, Wallace Carruthers of DuPont Labs invented nylon, the first synthetic fiber. Guaranteed not to run or tear, this polymer extraordinaire not only proved to be durable, but made a genuine fashion statement.
Some tools.
What you working on?
Well, the chain on Kim's bike keeps slipping and we have to go to the park.
Sure, help yourself. You know where they are.
Hey, why'd you do that? Don't throw that in there. Why not? It's garbage, isn't it? Not in our house. We recycle plastic bottles and containers.
Recycle plastic? How can you recycle plastic?
Well, they turn into all kinds of stuff like lawn furniture and insulation and even thread. My dad has a friend who's an environmental engineer, and he told me all about this stuff.
But what's plastic made out of anyway?
I think it's made from trees, you know, like rubber. I don't know. Dad probably knows. Dad, what do they make plastics from?
Well, most of the plastics we use today are made from oil.
You mean that black gloopy stuff that comes from the ground?
That's right. Same stuff we put in cars and they make gasoline out of. And in fact, the gum that you've been chewing on, Kim, is made out of plastic too.
Ew, you mean I'm chewing oil?
Well, not really. It's sort of like when you write on paper, right? You're not writing on tree bark, but they make it from wood. So it's processed.
But how do they turn the liquid oil into solid plastic?
Well, they do it by something called polymerization, which is kind of a complicated thing. They take the oil molecules and they split them up and they put them back together again. They make chains out of them. You know what? It's a lot easier to show you if you have a minute. We could do a quick polymer right here.
Okay.
If you want to try it. Okay.
Sure.
Why don't you get me the bowl and the beakers, and Ting, why don't you get the glue, and Kim, you can get the laundry detergent. Let me get some of this stuff out of the way here.
Well,
you know, polymers are just a rearrangement of building blocks. And glue works, well, you know what glue does, right? Well, glue is kind of sticky stuff, right? All right, well, why don't you pour some of that glue right in the bowl, Ting? And hold that for Olivia so it doesn't fall over. And I'm going to take some of this laundry detergent. And by adding certain chemicals, they can make the polymers, the one material, change into a different kind of material. So I'm going to add this in here. And why don't you take the spoon and do some stirring while I add some water. So I'm going to make this laundry detergent solution here. All right, and we want to get that all dissolved in there. Now, it's a good idea if you're going to do experiments like this. You always want to be protected because some of this stuff can be a little bit sore on your hands. It will make it maybe break out in a rash. So why don't you get some gloves on. All right, how you doing, Libby?
Okay.
All right, we got that mostly mixed up. Now, why don't you put the gloves on too, and I'll add a little bit more. Now, what you're going to have to do with this is going to be kind of cool. You got to sort of dig right in and pretend that you're making like dough or something. So you're going to start squeezing this stuff. Let me add this. Now, watch what happens as I put this into the glue. All right. Doesn't look like anything's going on yet, right?
Mm-mm.
All right. Now, why don't you start working that in there? Just stick your hands right in there. I'll pour a little bit more of the detergent in. How's that feel?
Hard. Getting hard like rubber.
All right. What do you think? Get in there, Olivia. Let's see what you can do with that.
Ew.
You want to grab a piece of it and sort of roll it around in your hands. And keep putting it back in the solution. Dip it in, then work it in your hands a little bit more and dip it in. Okay? And you see how stiff it's getting, right? It's not very sticky anymore. Dip it back in there. Here, let me get a piece of that out of there. Hold on. Let me get from the bottom. Okay, and if you work it into a ball, all right, and you get it really, really tight. All right, watch. Stand back. I don't know where this is going to go. okay, bounces right off. So what we basically made is what?
Glue balls.
Glue balls, okay? And you can make, polymer glue balls out of just using white glue. Now, one of the other reasons we use polymers is that they're very, very flexible. And why don't you take your gloves off and you could just throw them off to the side and dry off your hands. Let me get a balloon here. I've done this trick a lot of times for Olivia, so she knows the secret. But you've probably seen this done by a magician. If you take a balloon, now a balloon is made out of polymers. In fact, a lot of the same plastic that's in balloon is what's in your gum. So if you ever run out of gum, you can just sort of chew on a balloon. I guess it would be the same thing. All right, now, you know, if I take a sharp thing like a needle or a coat hanger here into a balloon, what's going to happen to it?
It's going to pop.
Okay, but if I get it just in the right spot, in the bottom here, where the polymer isn't too stretched out, all right, I can push it right in, and I'm leaking a little bit more than I usually do. And we go through the top, and basically, we have a balloon kebab. Okay, you go right through the balloon without popping it. And that's because the polymer is so flexible, it just sort of works its way around. You can see it sealed itself right up around the needle here. Now, the other thing that's good about polymers, the other advantage, is they're very, very strong and lightweight. So we can use them in a lot of places where we used to use heavy material. And I was working on this anvil here. You want to come over here? I can show you what we're going to do.
Okay.
We have on here right now some cotton rope. Now, normally I would never use cotton to try to lift up something like an anvil. This anvil weighs about 150 pounds. And cotton is a natural fiber, but it's not very strong. So I'll show you what I mean. I have this tackle here, and why don't you hold on to that? We're going to see what happens. Now, this anvil weighs about 150 pounds, so why don't you give it a tug, and let's see what happens. Okay, what happened to the rope?
It broke.
Yeah, because cotton isn't very, very strong. But if you turn around behind you, Ting, hand me that nylon rope. And this is why most of the ropes we use for heavy lifting are made out of things like nylon and polypropylene. These are different kinds of polymers. And they're much stronger. And they're lighter weight. You can see this one is a little bit thinner than the than the cotton rope. So what do you think? A thinner rope, what should happen?
It should lift up the anvil.
Well, yeah. It starts out as being thinner, but it is also a lot stronger. So let me get this through here. And got a couple of knots I have to take out. Okay, and I'll just pull that right through. All right. And, all right, now let's go. On a count of three again. 1, 2, 3, lift. Okay, and you see, you could move the anvil. Didn't break that time because the nylon is a lot more flexible. It's also stronger. But, you know, I got a friend, Joyce, who's a chemist out at Ethyl Corporation. I was with her last week. And they do all sorts of stuff, the polymers out there. And we could take a look at what I found out if you want.
Okay, cool.
All right, great. We're talking polymers today. And what is a polymer? Can you define it for us in real-life terms, Joyce?
Well, a polymer is a large molecule that is made up of smaller chemical building blocks that are called monomers. The monomers can be arranged into a chain, and that will give you a very flexible polymer. The chains can also be connected to each other. That's called cross-linking, and that will give you a rigid polymer.
So it's really like a building block. You can take a small, simple structure, and then just by the way you arrange it, you get a lot of different other structures out of it. Now, are there any natural polymers, or is this just a kind of a new invention?
There are many natural polymers. Cellulose is the most abundant natural polymer. Cellulose is the major component of plant cell walls. So cellulose would be cotton fibers, wood, paper.
So a tree would be a polymer?
And you're a polymer. Proteins are polymers.
Polymer? Oh, okay. Never thought of it that way. Now, in terms of synthetic polymers, we can use them to do a lot of different things. That's one of the reasons that people have gotten into plastics and such. What are some of the things that we can use polymers in today?
Well, polymers can be made into films, which protect meat. They can be made into plastic pipe, PVC pipe.
So all of these things here really are just different varieties of polymers. We have paint and glue and the old sandwich bag and pipe and things like that. In terms of what Ethyl does, you don't make plastics here, right? You do something to the plastics.
What Ethyl manufactures are what are called plastics additives. They're chemicals that are added to plastics to modify the properties.
Could you give me like one example of one thing you might add and the process that it goes through?
Well, Ethyl makes flame retardants, and flame retardants are added to plastics that the polymer manufacturers manufacture.
So is this stuff here, this is raw plastic.
This is raw plastic.
Where does it go from here?
The raw plastic is combined with a flame retardant in a machine called an extruder, and it's mixed together. It's almost like mixing dough, and you form a thin ribbon, which is cooled in the water, and then the ribbon is chopped into small pieces, and it makes a plastic that can be molded into a part.
Now, what made you want to be a chemist? I mean, you know, how did you get into this?
Well, I never really decided to be a chemist. I took a lot of science and mathematics classes when I was in school, and I always liked them, so I took more and more of them. So I came out with a PhD in chemistry. I really like chemistry. I started working for a chemical company.
So you just sort of evolved into it. Nobody just said, be a chemist. You said,
that's right.
It just sort of happened. It was exciting for you. And so, well, that's great, Joyce. Thanks a lot for letting me come out and mess around and see the lab. And we'll talk to you again soon.
Great.
All right, thanks. So what'd you think of Ethyl Corporation?
I didn't know that so many different things were polymers.
Yeah, there are a lot.
I didn't know that I was a polymer. I thought I was a person.
Well, you're sort of like a protein, person, polymer, all put together in different ways type of thing. But the nice thing about polymers, you can really do so much with them. You can make them into pitchers and bowls, and even, you know, rubber chickens can be polymers. So, but I'll tell you, I got a challenge for you. Let's see if you can figure this one out. One of the nice things about polymers, we were talking about bounciness, we can measure the coefficient of restitution of different polymers. So,
The coefficient of what?
coefficient of restitution. You know, bounciness.
That's what I like about my dad and his science friends. They take something simple and they stick a big word on it so it sounds important.
Well, actually, it's like learning a language. You know, when you go to a foreign country, you got to learn the words first before you know what's going on. In science, you got to learn the words before you can figure it out something. But coefficient of restitution really just means how much a polymer will bounce. And we can do that right here with a quick demonstration. Why don't you hop up on the platform there, Olivia. Now, take this ball. I'm going to start with the pink one. I want you to hold it up all the way. And now I want you to watch it as she drops it. See how far back it bounces. Ready? Go ahead. All right. About how far up did it bounce?
Halfway.
About halfway. Okay, so that ball has a coefficient of restitution of 50%, about halfway. Now let's try the blue ball. All right. How about that one?
44.
Yeah. Now this is about 75%. Now we're going to go to the tennis ball. All right. Put that one back in there. All right. Ready?
About a quarter.
About a quarter, yeah. So this one has a coefficient of restitution of about 25%. Now, of these three balls, which do you think has the most elastic polymer in it?
The blue one.
The blue one. Higher the coefficient of restitution, the more elasticity. Now, Kim, why don't you turn around? Give me that bowl. I have some eggs in there. And these kind of weird eggs because they've been sitting there soaking in vinegar for the last day or so. Now, most of the time, when you take an egg and you drop it, right, what do you have?
It's going to shatter.
Yeah, all right, we have the coefficient of splatter. So, you know, we go, whoa!
Whoa!
You got that. Now we'll have a little bit of mess. That's all right. But these eggs, I've been working on them, and I won't drop them. Dry your hands off there. I won't drop them as far, but watch it. All right, the shell on this thing has been turned. It's actually been dissolved. The vinegar has changed it, and it's almost like a polymer. It's almost rubber now, so it will actually bounce. And in fact, yeah, if I use this, if I keep it in here for another day or so, I would be able to drop this egg from almost the same height as I dropped the other one, and it wouldn't break. So this is one you can try. It's a very nice one. Just stick it in vinegar. So that's it for polymers. So I hope you go and get your bike fixed now and have a good time at the park, and I'll see you soon.
Thanks, Dad. But can we get some of that glue goop? We want to try it out at the park on the tennis court.
Sure, be my guest.
Come on, let's go check out the coefficient of cuteness, some of the guys playing basketball.
What a mess. You see what you did? You see what you did?
Here's a cool way to demonstrate the strength and flexibility of polymers. Get a zipper top sandwich bag and fill it full of water. Zip it closed and take a really sharp pencil. If you get it just right, you can stick the pencil right through the bag without spilling a drop. See how many pencils you can get through the bag without it breaking.